Additive manufacturing is a manufacturing method that is increasingly growing in application and becoming widely available at a low barrier to entry. Among various types of additive manufacturing, material extrusion is most prolific amongst the consumer market, as material extrusion machines can cost as little as $200. Although inexpensive, material extrusion does have its current limitations. This is a technique where a thermoplastic filament is continuously fed from a spool through a heated nozzle. The material is melted and extruded onto a build platform where it cools and solidifies to form a layer of the object. The build platform then lowers, or the nozzle is raised, and the nozzle adds subsequent layers, adhering them to the previous ones. Inherently, there are several modes of deformation due to layer bonding and the adhesion between passes. Four main parameters govern the application of material extrusion: time, material properties, precision, and cost. Each of these parameters can be viewed as an optimization problem, as increasing one parameter may cause an effect on another parameter negatively. In this presentation, we review methods that can be implemented to improve precision and material properties while being conscious of their effect on other parameters.
The specific aim of this project is to explore technological advancements in material science and additive manufacturing processes to improve the structural properties of produced parts. We have two hypotheses in this project. Additive manufacturing creates layers that are bonded together. The bond between layers can be a location of weakness. The first hypothesis is that if material extruded parts are treated with a vapor smoothing process, the bond layers will be stronger, because the process will smooth out sharp edges and the origin of cracks. Next, if additive manufactured parts are annealed, then material properties such as strength and toughness will improve because of the reduced internal stresses, but there will be unwanted dimensional changes such as warping and shrinking. Our second hypothesis is that if composite reinforced plastics are used, the added composite structure will reduce dimensional changes while still retaining the benefits of annealing.
The significance of the innovations and research proposed in this presentation is that recently much more attention has been paid to material extrusion additive manufacturing as a serious method to manufacture end-use products. The proposed research aims to provide methods to address several critical issues and barriers that plague material extrusion and have prevented widespread adoption as a primary manufacturing process. Some of these critical issues, which are shown on the right, include poor layer adhesion, which would include issues where the poor bonding between layers leads to unsuccessful prints, wasted resources, and increased production times. Residual stresses, which typically lead to premature failure in manufactured components. Availability of material options, as a preferred material may not be readily available off the shelf, leading to the need to create a custom filament with high costs. And surface roughness issues. If a print doesn't look good, it may not be viable for end use, and a poor surface finish could also create undesirable friction while in use, also causing premature failure.
Okay, a quick intro into vapor smoothing. In this process, a plastic part is exposed to a solvent vapor which absorbs into the plastic and partially dissolves the surface of the part. Figure 1 is an illustration of what this process would look like. Now, vapor smoothing has the effect where it causes plastic parts to become smoother and glossier, so definitely good aesthetic effects. It also reduces sharp edges on the surface. Now this can cause defects such as drooping, but it does have some good effects when you zoom in. The figure on the bottom shows the layer lines of a MEX part being smoothed out with vapor smoothing. Now this can increase part strength by reducing small cracks that could cause weak spots when a load is applied. Okay, on to thermal annealing. The theory is that MEX parts contain internal stresses due to the rapid heating and cooling during fabrication, and removing these stresses could increase strength. In the annealing process, parts are heated to near or above the glass transition temperature to partially melt or soften the plastic and allow the internal stresses to dissipate. Now this has the effect of increasing part strength, toughness, and Young's modulus. Now you are softening the plastic, so some shifting and warping can happen, but some advantageous shifts happen, such as in the bond between layers. Now the bottom figure on the right shows an extreme best case scenario where a part is annealed so well it no longer breaks on just the layer lines during a dog bone tension test, and showing a clear strength gain. Moving on to the use of carbon fiber composites. Adding up to around 30% carbon fiber to MEX filament increases part stiffness and strength just like it does with the normal epoxy-based carbon fiber parts. And vapor smoothing and thermal annealing will only affect the plastic and not the carbon fibers. The idea behind this is that we can use a more aggressive post-processing recipe on carbon fiber reinforced parts, since the carbon fiber will resist the unwanted effects. The fibers will reinforce sharp edges through a vapor smoothing process and prevent shifting and warping during thermal annealing.
Several manufacturers offer closed-loop monitoring of the print head on industrial machines, such as the Hadge 3D X1 and the Mark Forged X7. But what about monitoring the actual print? Defects can be a function of lack of real-time monitoring and correction. In theory, material extrusion can achieve a breakthrough in mass adoption if these defects can either be removed completely or detected and corrected. This can save time by catching defects hours earlier and either manually correcting the issue or even automating the corrective process. One novel, inexpensive method that has been used for monitoring defects has been acoustic monitoring. In this method, the hypothesis was that ambient audio can be digitally removed and the sound of the machine can be isolated. Then, using machine learning, the acoustic sensor can determine whether the part has crack propagations via differences in audible feedback to the sensor. By comparing the resonant frequency of the part without cracks to the part with cracks, theoretically this method of defect monitoring is achievable. Another method that has been used for monitoring defects has been infrared thermal vision. Thermal monitoring can detect deposition errors, inconsistencies in the feedstock, lack of bonding, and poor printer parameter settings. Finally, various optical sensor configurations have been researched in monitoring defects. Some configurations mount the camera to the nozzle assembly, whereas others mount the camera to the base. Additional sensors can be added as well, such as a second camera or even lasers. Using a laser or a second camera can help the system triangulate the location that is being viewed, increasing accuracy and precision. To review these different types of defect monitoring, a decision table has been created. To compare the alternatives, 4 categories are considered: calibration, precision, cost, and accuracy. Each of the 6 alternatives are weighted in each of these categories, and then 3 scenarios are put together. Scenario 1 is for the hobbyist. This is a cost-effective, cheap alternative with decent monitoring capabilities. In Scenario 2 and 3, these are 2 industrial options with different weightings to calibration, precision, and accuracy. Using these weightings, the best alternative for the hobbyist is the base plate mounted optical sensor. Using the weightings in Scenario 2, the best alternative for the industrial option is the base plate mounted optical sensor. In Scenario 3, the double nozzle mounted optical sensors.
Innovations. We are working on developing high-performance materials that ensure smooth extrusion and robust layer adhesion. Our secret sauce is optimizing rheological properties for reliability and efficiency, but that's not all. We're introducing advanced alloys crafted for ME durability. These alloys not only reduce thermal expansion but also bring in real-time adaptability with smart alloys. And of course, sustainability is at the core. We are driving eco-friendly practices by incorporating recycled content and environmentally conscious alloys. As we move on to our second slide, let's explore how we are incorporating advances in layer bonding, monitoring, and post-processing, essential pillars in MEX technology. We are utilizing cutting-edge computational models and real-time feedback to optimize layer bonding. The aim is to tailor post-processing techniques for most uniform strength distribution, addressing anisotropy, a game changer in MEX structural integrity. Next, proactive defect monitoring takes center stage. Our approach involves integrating advanced sensors and machine learning for real-time defect detection. The implementation of closed-loop control system ensure dynamic adjustments, ensuring continuous optimization during the entire printing process. We are exploring various monitoring techniques from optical and acoustic methods to innovative approaches like acoustic monitoring. The potential application of computer vision in MEX are particularly exciting, opening new avenues for defect detection. Lastly, strength-focused post-processing. We are addressing vulnerabilities head-on with the techniques like vapor smoothing and thermal annealing. By considering composite materials, we are ensuring optical strength and geometry in every MEX creation. In conclusion, these advances collectively contribute to a significant impact, improving mechanical properties and elevating the overall strength of MEX created part. The future of MEX is not just promising, it's transformative.
Project approach. Our approach navigates to comprehensive testing method for structural improvement. We are employing ASTM standardized tests to gather empirical data. Our testing arsenals include hardness, thermal, tensile, compression, fatigue, creep, impact, and chemical resistance. Each method faces scrutiny against control samples for a comprehensive and meticulous analysis. Secondly, we are evaluating composite and alloy materials using ASTM testing methods such that we ensure a focus on structural properties. Layer bonding optimization. Now layer bonding is a puzzle and we are solving it through sophisticated printing algorithm. Optimization is the name of the game, tweaking printing patterns, infill density, air gap print speed, and build volume temperature. Simulation and testing are tools of choice to evaluate the quality of layer bonding. Defect monitoring enhancement. Improved defect monitoring is on the agenda. Compare rigorously with control paths. We are crunching numbers, analyzing statistical probability of defects without monitoring. Our testing methods in line with ASTM standards provide backbone for evaluating structural properties improvement. Lastly, post-processing techniques. We are dwelling into post-processing integrates vapor smoothing samples in ethyl acetate for varying duration. Each MEX part is printed individually using identical recipes for consistency. Our testing spectrum covers a range from control samples to vapor smoothed, thermally annealed, and combined treatment. A diverse testing suite ensures a robust foundation for empirical data collection and subsequent analysis.
We conclude this presentation on the groundbreaking research in additive manufacturing, particularly focusing on material extrusion or MEX. Let's reflect on the key insights and innovations that shape the future of manufacturing. Firstly, we have delved deep into the critical challenges that have hindered the widespread adoption of MEX. Challenges like layer bonding, residual stress, and surface roughness have been at the forefront of our exploration. Our journey led us to innovate in various dimensions, from crafting high-performance composite materials tailored for MEX to refining layer bonding through advanced computational models. We have left no stone unturned in enhancing the structural properties of MEX-produced parts, but one of the most exciting breakthroughs is our defect monitoring revolution. Imagine a system that not only identifies defects in real time, but also corrects them as the printing process unfolds. Our use of advanced sensors and machine learning creates a proactive approach, reducing weakness between layers and strengthening the very foundation of MEX parts. Let's move on to our next few key insights in this project. Our focus on tailored composite solutions opens new doors for MEX applications. These composites optimize rheological properties, ensuring smooth extrusion and improved layer adhesion. This isn't just about materials, it's about crafting the future of manufacturing with precision and versatility. Precision in layer bonding has been another hallmark for our research. Advanced computational models, real-time feedback systems, and tailored post-processing techniques converge to mitigate anisotropic properties. This not only enhances layer bonding but contributes to a more uniform distribution of strength within printed parts. As we navigate the delicate balance of post-processing, vapor smoothing, and annealing techniques, we seek to strengthen MEX parts while preserving their geometric integrity. We are not just improving materials, we are shaping a process that combines strength and precision in a delicate dance. Let's get into the slide impact and future directions. Firstly, industrial transformation. Addressing these challenges unlocks material extrusion's full potential, offering custom, complex, and cost-effective manufacturing solutions. This has a profound impact on industries reliant on high-quality components such as aerospace, healthcare, and automotive. Second, the standardization and sustainability. Our project pioneers standardized post-processing techniques, reducing waste and increasing the efficiency of material extrusion processes. The integration of sustainable materials aligns with environmental considerations as adhering in a new era of responsible additive manufacturing. Lastly, the continuous advancements. The journey doesn't end here. We have set the stage for ongoing advancements in AM technology. Our research lays the groundwork for standardizing best practices, expanding material choices, and enhancing product performance. Thank you for joining us on this transformative journey in the world of additive manufacturing. Together, let's shape the future of manufacturing through innovation and precision.